Hello everyone. Today we'll be discussing about applications of Gauss's theorem. The first application is to find the electric field due to an infinitely long thin charged wire. Suppose this is your infinitely long thin charged wire. With linear charge density, say lambda. Now, we know that the electric field lines, they go away from the positive charge. So, to draw the Gaussian surface, there is an imaginary surface. You'll have to take the points at an equal distance from the wire. Suppose let us say it is R at this point. At this point, if you imagine is the field line that is going away from the positive charge, it will form a cylinder. The Gaussian surface will be a cylinder, like this will look, and this cylinder will be called as the Gaussian surface. Let us take the length of the cylinder as L. Then if you look at the cylinder, then you will find there are three surfaces of the cylinder. This is the curved surface, the middle part. This is the flat surface, circular. This is also flat surface, circular. So in these three faces, we will take an area element. Let us take here one on the curved surface, ds. Here we'll take another one, ds, on the flat surface towards the right, and the third one, let us take here ds on the left surface. And as we know, the area vector is normal to it, n cap. Let me represent it, n cap, normal to the surface you have to draw. Then you will focus about the electric field line, which direction it is going. For a straight wire, it is going up, it is going towards you, it is coming towards me, it is coming down also, it is going equal in all the direction. But as we have chosen the surface area on the top, we will take the electric field line going towards the up direction. So the electric field line direction is this side. In this case also, this area element you took above the wire, so the electric field intensity or electric field line will be pointing this side. Here the area vector and the electric field, they are at 90 degrees to each other. Here the angle between them is 0 degree, and here also you have chosen up. If you choose here down, then it will go perpendicularly downside. Area vector will be pointing towards the left. Whether you take up or down, it will be perpendicular to each other, area vector and the electric field. Now to apply or to use Gauss's theorem, first of all, you recall back your Gauss's theorem. Electric flux E, that is equal to surface integration of E dot ds is equal to net charge divided by epsilon naught. This is your Gauss theorem. Now, first of all, this electric flux you have to find out for the three surfaces. After that, you have to equate it to 1 by epsilon times the net charge. So to find out the flux, net electric flux E is equal to surface integration for the closed surface, that is for the cylinder, E dot ds. You can write this as surface integration of E ds cos theta. So this one, as we have three different surfaces, we will divide it into three parts. The first one, so E phi is equal to first one, we will represent this as A, this one will represent it as B, and this point will take it as C. So along A, E ds cos theta, along B, E ds cos theta, and along C, E ds cos theta. Now put the angles accordingly. The angle between the electric field and the area vector at A and B, it is 90 degree, whereas at C it is 0 degree. So these two are 90 degree. You can write this as EDS cos 0 degree. At A it is 90 degree, sorry. At B, EDS cos 90 degree. And at C, it is EDS cos 0 degree. So these two values will vanish because cos 90 is 0, this is also 0. The only term remaining will be this one, that is at C, E, ds. Now E is a constant term here, integration is for the surface area. E, surface area of what? This is at C. Surface area, curved surface area only is remaining. Curved surface area, your formula is 2 pi RL. Like this you can find out the electric flux. After you find out the electric flux, then you can use Gauss theorem. Let us keep the result here. There is the electric flux. Using Gauss theorem, electric flux phi E is equal to 1 by epsilon naught times the net charge. Now, electric flux you found out already, is E 2 pi RL. This is 1 by epsilon naught. The charge, you convert it. If you try to introduce linear charge density lambda, so equal to charge per unit length, so charge will be equal to linear charge density into L. So write linear charge density into L. This L, if we cancel it out, then you get the expression for electric field intensity. It will be 1 by 2 pi epsilon naught, is 2 pi epsilon naught and R. On top you have lambda. So this gives us the expression for electric field intensity due to a long thin charged wire. If you plot it graphically, your graph will look like this. This is distance R. Ultimately we took the surface area, curved surface area, this one. The distance of the curved surface area is R from the charged wire. So this gives us in vector form, vectorially you can write it as lambda divided by 2 pi epsilon naught R cap. Like this also you can write. This is in vector form. And then electric field intensity here is inversely proportional to the distance. Inversely proportional to the distance. So graphically, if you represent E along y-axis and R along x-axis, then as it is inversely proportional, the curve will fall down this way to come graphically. Now let us see the second one, that is field. The second application, field due to an infinitely thin charged plane shift. In this case, you take the infinitely thin charge sheet like this. Charges are distributed on its surface. We'll take a certain area of cross section. We'll write it as A. In this case, also the electric field lines will be pointing towards the right as well as it will be pointing towards the left. So if you choose the circular cross section like this, the Gaussian surface will be cylinder here as well. Let us take the length of the cylinder as 2r, so that here it will be r, here also it will be r. This is divided into two parts. We are taking an equal distance because Gaussian surface must be symmetric. This is your Gaussian surface. Now in this case also you will choose the areas, surface areas. Here I have chosen one, for instance. Here I have chosen right side ds. This is also ds. This is also ds. Here I will write A. This is at point B. This is at point C. Area vectors will mark it n cap perpendicular to their respective surfaces. Then the electric field direction here is from left to right. This side from right to left. So in this case, the electric field direction is this way. This side is showing, it's making an angle of 90 degree here. But towards the right at point A, electric field line is along the direction of area vector. Towards our left also the electric field line is along the direction of area vector. Here the angle between them is 0 degree. Here also it is 0 degree, but here it is 90 degree at point C. So in this case, if you find out the net flux, phi E is equal to surface integration of E dot ds. This will be integration of E ds cos theta. So this one also will divide into three different surfaces, A, B and C. First for A I am writing E ds cos at A the angle is 0 degree, plus at point B also it is 0 degree. E ds cos 0 degree, but at point C it is 90 degree. Angle between E and ds angle is 90 degree. So this third term C will vanish because cos 90 is 0, so everything will become 0. This is 1, cos 0 is 1, cos 0 is 1, so EDS at A and B will remain. So at A EDS you have, then at B also you have EDS. Now in both the cases, E, if you take it out, the surface area, here we have chosen the surface area to be A. Here we have chosen it to be A. So here also it will remain as A. Here also it will remain as A. The surface area will remain as A. So the net surface area will be A plus here also E into this will give us A. So ultimately you will get 2EA. So this is the net flux around the Gaussian surface. Now we'll use our Gauss theorem. When we use our Gauss theorem here, the net flux is equal to 1 by epsilon naught times the net charge. The net charge, this net flux, we got it as 2EA. The net charge here, the surface charge density is equal to charge per unit area. So charge is equal to surface charge density into area. So we write surface charge density into area. This area will get cancelled. Then you will get E is equal to sigma divided by 2 epsilon naught. I think all of you can remember what is epsilon naught. It's permittivity in free space. Here sigma is the surface charge density around this area of the plane sheet. In this case, E is not proportional to the distance. We found out this 2EA from these two ends. This distance has nothing to do when we find out the electric field intensity due to charge plane sheet. So there is no R. Now the third application, let us see. In the third application, to find the electric field due to a charged spherical cell. Or you can call it as a charged sphere. In case of a charged sphere, suppose this is your charged sphere. Charges are distributed on the surface. Three cases will arise because in a shell, inside is hollow, inside, then outside you can find out the electric field, and you can find even on the surface of the sphere. So one by one let us see. Case 1. Field, that is electric field intensity outside the sphere. If I take the radius of the sphere as R, then to draw the Gaussian surface outside, field lines are going away. So at an equal spacing, at an equal distance, I can take a surface at an equal distance from the sphere at all the points. Let us say the radius or the distance is R. Now on this Gaussian surface, if you select an area element here on the surface, ds, then the area vector will be pointing in this direction. And the electric field line, we know that it goes away from positive to infinity. It goes radially. So the area vector also, the electric field also will point in the same direction. You can take this area element anywhere on the surface as you like. Everywhere it will remain the same because here also electric field line is passing this way. If I take one area here, area vector also will point in the same direction. Angle between E and ds will be 0 degree. Let us see, in this case, R is less than R, capital R is less than small r. In this case, if we find out the net electric flux E dot ds, E ds cos theta, what we'll find is there is only one surface, so I'm going to divide into 2-3 parts. Cos theta is here 0 degree, so we'll write like this: E ds cos 0 degree. Cos 0 degree is equal to 1, so you get E ds. Then E you can take it out, surface integration of ds, surface integration sum of ds, when you say the surface area of the sphere with radius small r, so it will be 4 pi r squared. Your mensuration formula you can use. This is the net flux on the outside the sphere. Now if you use Gauss theorem, to use Gauss theorem, the net electric flux is equal to 1 by epsilon times the net charge. And the net electric flux, we got it as E 4 pi small r square, and that is equal to 1 by epsilon naught. Here also surface charge density is equal to charge per unit area. Charge will be surface charge density into area. Surface charge density into area. So the electric field intensity is equal to 1 by epsilon naught here. Sigma A, the area of the surface charge is 4 pi capital R square. Charges are distributed over the surface, so it will be 4 pi capital R square in place of this area. And then downside, you bring down this 4 pi R square. 4 pi, if you cancel it, you will get the electric field intensity outside that means outside the spherical shell. That is sigma. Here we can write sigma R square by R square. So this will give us the electric field intensity outside the shell. Now let us see the second case, that is case 2. Field on the sphere. Case 2, field on the sphere, that is R and R both are equal. So in this case, from this, if you can remember, you can write down if capital R and small r both are equal, that means this surface is brought here now, then both will coincide. In that case, electric field intensity is equal to sigma R square by epsilon naught R square. It will be equal to sigma divided by epsilon naught. You will get maximum electric field intensity on the sphere. This is the maximum value of E. You will get it on the sphere. Now let us go on to the third case. That is case 3. Here what we have done is these two, since R is equal to R, both will get cancelled. So the remainder is sigma divided by epsilon naught. Then in case 3, let us find out the field inside the spherical shell. Inside the spherical shell, we cannot draw Gaussian surface because the field line does not come inside. So in this case, this small r is less. You can just imagine small r is less than capital R, or in other words, R is bigger than R. Now, if you take this capital R bigger than small r, as inside the body there is no charge, the net charge Q net is equal to 0 inside the shell. So electric flux, or if you say E times the area, that is 4 pi R square, that will be equal to 1 by epsilon naught the net charge. The net charge is 0. 0 by epsilon naught will give you 0. So ultimately the electric field intensity 0 divided by 4 pi R square also will become 0. So electric field intensity is not present inside the charged spherical shell. To conclude it, if we represent these three cases graphically, then we can represent like this. This is R along x-axis, electric field intensity along y-axis. Then the first case, as we know, E is inversely proportional to R square. We can represent it this way. This is inversely proportional to distance square. Then the second case, that is your maximum value of E can be represented from the peak of the curve, the E maximum. And for the third case, electric field intensity is 0. So this curve will also indicate here E is equal to 0 at the center. At the center, that means inside the charged spherical shell. With this, we have come to the end of this chapter, that is electric charges and fields. Thank you and have a nice day.